So we claim that first is that mu k is finite for all k compact. This follows immediately because it is the infimum of lambda f's and all these lambda f's are finite. So mu k is finite. Second is that mu is irregular on open sets. So how do we show this? So let U be open in X, and suppose that let alpha be chosen such that it is less than mu U. So this implies that there exists f less than u such that alpha less than lambda f less than mu u, because mu u is the supremum of all such f's, all such lambda f's, and so if you choose any alpha less than mu u, there will be something in between, lying in between mu u and alpha. So now we have that alpha less than lambda f less than mu u. Now we will show that if k is chosen to be the support of f, which is compact, then let me write it, alpha less than mu k less than mu u. So this will show that, actually I am proving the second part. So I claim again here that if we choose k to be the compact set support of f, then alpha less than mu k less than mu u, and this implies that mu is irregular for u, right? So why should this be true? So if G is a continuous function with compact support such that k is less than G, then lambda f is less than or equal to lambda G, because f is 0 outside of k and G is 1 on k, and f takes the maximum value 1. So this means that lambda f is less than or equal to lambda G. So since alpha is less than lambda f is less than mu u, this implies that alpha is less than mu k is less than mu u by taking infimum over k less than G on the right hand side. So we showed that mu is irregular on open sets. Now we come to the last claim, which was that lambda f is actually given by the integral of f with respect to this d mu lambda. So of course our mu lambda is the mu that we wrote, and to show this we note that it suffices to show this for f in CCX, but with range in 0 1, because since CCX is a linear span, rather any element of CCX, any element of CCX can be expressed as a finite linear combination, so with complex coefficients complex coefficients of elements in CCX01. Because f is compactly supported and continuous, it has a minimum and a maximum, and so we can partition the range into various pieces of size 1, and then we can simply write any element of CCX as a finite linear combination of elements in CCX with range in 0, 1. So let us take a function, take a function f which is continuous compactly supported with values in the interval 0, 1. So we denote K0 to be the support of f, which is compact. Now we will define a sequence of compact sets Kj, j equal to 1 to n for each n in n, and we will define and also a sequence of functions fj, which will be again in C0x01. So this is again a sequence j equal to 1 to n, and such that we will have 1 over n sum j equal to 1 to n mu of kj is less than equal to integral fj d mu over x, which is less than or equal to 1 over n j equal to 0 to n minus 1 mu of k j minus 1. And similarly we will have the same inequality for lambda of fj, mu kj less than or equal to lambda of fj, and this is less than or equal to j equal to 0 to n minus 1 mu of kj minus 1. And this sequence of functions fj j equal to 1 to n will satisfy, so there is no summation here, no summation yet. So these are the inequalities that we have, and these fj's will satisfy that f, the function f that we started out with, is the sum of all these fj, and so this would imply that 1 over n, if you sum these inequalities, so this is for each j, in 1, 2 up to n. So if you sum all these inequalities, all these are non-negative numbers, so you can sum all these inequalities and you will get on the left hand side sum of mu kj j equal to 1 to n, and in the middle you will get, for the first one you will get f d mu, because f is the sum of fj's, and on the right hand side you will get sum j equal to 0 to n minus 1 mu of kj. And similarly we also have the same inequalities for lambda of f. So you will have mu kj j equal to 1 to n on the left, lambda f, and then on the right you have the sum j equal to 0 to n minus 1 mu kj. So this implies that the difference lambda f minus f d mu has absolute value less than or equal to 1 over n mu of k0 minus mu of kn from just by subtracting this inequality with the one for integral f d mu. So since this is equal to 1 over n mu of k0 minus kn, and this is less than or equal to 1 over n mu of support of f, which is k0. So this part is finite and n is arbitrary, so this goes to 0 as capital N goes to infinity, which implies that these two things are equal. So now we have to just build up our sequence of compact sets kj and our sequence of functions fj such that they satisfy these inequalities, as well as that f is the sum over all these fj's. F is the sum over all these fj's. So we will use the following formula. So let kj be the set of points in x such that fx is greater than or equal to j over n for each j between 1 to n, and fj is equal to the minimum of the maximum of f minus j minus 1 over n comma 0. You take the maximum of these two things and the minimum of this value and 1 over n. So one has to check that. So this is an exercise. Check that f equals sum over fj, j equal to 1 to n. So let's see what these fj's look like. So let us suppose that x is our real line, and we have a nice function, bell shaped function with compact support given by the interval a to b, and the height is exactly equal to 1. So let's see what we have done. First of all, we have divided this range into parts of length 1 over n. So this is 1 over n, and so we have divided the whole thing like this. So each has width or height 1 over n. So now let's see what is our f1. So j equal to 1, for j equal to 1, f1 is the minimum of the maximum of f minus j minus 1 over n, so it's 0, comma 1 over n, 1 over n. So this is nothing but the minimum of f comma 1 over n. So now let's see what is k1. This is equal to the set of all points such that fx is greater than or equal to 1 over n, which means that k1 is nothing but this set here. So if you take this point and if you take this point, then I'll denote the endpoints as a1 and b1, and within this interval a1 and b1, the value of fx is greater than or equal to this value 1 over n. So fx has values upwards of 1 over n. So this is our k1. So now let us see what kind of graph f1 has. So f1 is equal to f1 of x. So now we can have the partition. If if a less than or equal to x less than or equal to or less than a1, then we have that f1 is less than 1 over n. So f1 is simply f. So this is fx. Now if a1 less than or equal to x less than or equal to b1, then it will have, so in this region it is having this part in the graph, but in the interval a1 to b1 it is going to be constant, because we are taking the minimum of f and 1 by n, and on k1 the value of f is greater than 1 by n. So within k1 it's going to be constant. It takes the constant value 1 over n, and then again, so let me write it here, is 1 over n, and again if b1 less than x less than or equal to b, then again it is f of x. So this part of the graph is also part of f1. So this is f1. Now let us look at what kind of graph f2 has. It will be having a similar kind of graph. So now let us take j equal to 2, and we have f2 is the minimum. Now the maximum value of f minus 1 by n comma 0, and the minimum value of this value and 1 by n, and we have k2 is the set of all points such that fx is greater than or equal to 2 by n. So let us see what kind of set we get for k2. So this height is 2 by n, and so for k2 we will get this interval a2 b2, and this is k2. And now f2, if we take f2 x, then between 0 less than or equal to x less than or equal to a1, what do we get? So it is the maximum value of f minus 1 by n comma 0, but f minus 1 by n is negative in this region because f is less than or equal to 1 by n, and so this is going to be simply 0, and we take the minimum of 0 and 1 by n, so this is again 0. So this is between a and a1. Let's take between a1 and a2. Between a1 and a2 the function has value greater than 1 by n but less than 2 by n. So if you take the maximum of f minus 1 by n comma 0, you will get f minus 1 by n, and f minus 1 by n is still greater than 1 by n because it is less than or equal to 2 by n. So you will get fx minus 1 by n. So you are taking this this part. So let me take another color. So you are taking this part and you are pushing it down 1 by n. So this part is 0, this part is just the copy of the one in the green part above, and then we will have again 1 by n in this part in the for k2. So for a2 less than or equal to x less than or equal to b2, we will have simply 1 by n, and then again if b1 less than x less than b2 less than x less than b1, you will get fx minus 1 by n, and if b1 less than equal to x less than b, you will get f2x to be simply 0. So here in magenta color we will have up to here 1 by n, so this is 1 by n, and then again this part is dropped up to here, and then you get a 0. So this is the graph for f2. So in fact one can write down a general formula for fj. So fjx for j in 1 to up to n, we have fjx is equal to, this is equal to 0 if x does not belong to kj minus 1. So outside kj minus 1 this is going to be 0. If x belongs to kj minus 1 minus kj, notice that kj is a subset of kj minus 1 for each j, and for this case we will have fx minus j minus 1 over n, and finally if x belongs to kj, then it is going to be 1 over n. So this implies that we have the pointwise inequality 1 over n chi k j less than or equal to fj less than or equal to 1 over n chi kj minus 1, and we also have that f is equal to summation of fj, j equal to 1 to n, and if we integrate this inequality, we get 1 over n mu kj less than or equal to integral fj d mu less than or equal to 1 over n mu kj minus 1, and now we are going to use the fact that mu is radon to derive a similar formula for lambda fj. So since mu k is the infimum of all the lambda f such that k less than f, this implies that 1 over n mu kj is less than or equal to fj, lambda fj. This is because 1 over n chi kj less than or equal to fj. So this means that fj or rather kj is less than fj. So this implies 1 over n mu kj is less than or equal to lambda fj, and on the other hand we have that lambda fj is less than or equal to 1 over n mu u for any open u containing kj minus 1. This is because, simply because fj, since fj is equal to 0 outside kj minus 1. So this implies that kj less than fj less than u for any open u containing k j minus 1. Now by outer regularity, so this was property 2 that we proved before, property 2, and now by outer regularity we can approximate mu k j minus 1 with respect to the open sets, and so we can take the infimum on the right hand side. So we get 1 over n k mu kj is less than or equal to lambda fj is less than or equal to 1 over n mu kj minus 1, and this is what we wanted to show in order to derive our result. So let's go back to these two results. So one was this, when you sum up all the inequalities. So this was the first inequality that we needed, 1 over n mu kj less than or equal to integral fj d mu less than or equal to 1 over n mu kj minus 1, and similarly the same inequality for lambda in place of the Lebesgue integral. And now you sum it up and then you derive that lambda f minus integral f d mu is less than or equal to 1 over n mu k naught, which goes to 0 as n goes to infinity. So this finishes the proof of the fourth part, which said that lambda f is equal to integral of f d mu. Now we have to show one more thing, which is uniqueness. So suppose that mu prime is another radon measure on X such that lambda f is equal to integral x f d mu prime for all f in CCX. But then we have, so it suffices to show that mu prime equals mu, it suffices to show that mu prime u is given by the same formula of the supremum of lambda f such that f is less than u, and this was by definition our mu of u. So then we just have to show this result, and to show this result we proceed as follows. So if u is open, so this is for u open, if u is open and k a subset of u, a compact subset, and I am going to use the inner regularity of mu prime because it is a radon measure, inner regularity for open sets. So now by Urysohn's lemma, there exists f in CCX01 such that k less than f less than u, and this implies that because lambda f is given by the integral, this implies that mu k, if you integrate the indicator function, so let me write it in terms of indicator function. So chi k is less than or equal to f less than or equal to chi u, and now if you integrate, you get mu prime k less than or equal to integral f d mu prime, which is equal to lambda f, and this is less than or equal to mu prime of u. And now since mu prime is inner regular on open sets, this implies that mu prime u is the supremum of all such lambda f such that f is less than u, because the left hand side converges to mu prime u as you take an increasing sequence of compact subsets of u. So we have also proven uniqueness, and this finishes the proof of the Riesz representation theorem. And now in the next lecture we will see what kind of examples of measures we can construct out of the Riesz representation theorem.